So then it talks about how you can do the same thing with momentum as you've done with every other kind of vector, right?
Yeah.
So if you start out, this is your x, this is your y, you start out with a momentum like this, you can break it down into an x component. So this is px and py. So it's just like forces and acceleration. You can break it down into x and y components. Okay. So then what is impulse?
Impulse momentum?
No, just the idea, like the explanation of what impulse actually is. So it talks about it up here. So change in momentum is related to the time integral of the force.
So it does have to do with momentum.
Right. So if you this was your impulse, right?
Okay. Yeah.
This is a force. This is time. So what are the units of force?
Newtons.
Yeah. And that's made up of a kilogram times a meter per second squared. What are the units of time?
Seconds usually.
Yep. So if you were to take the area of this, that would mean you take the height of force times the width of S. So what would your units be for the area of this thing right there? Let's make it simpler. We don't have to find the area, but so say your impulse was just like perfectly square. You just went up like this, back down. So you wanted to find this area. So the impulse is the area under the force time graph. Okay. So basically they say, find this force, find out how long it acts, and multiply those two together. And that'll give you your impulse.
So just newtons times seconds.
Yeah. So for impulse, which is J, your units are newtons times seconds. And then newtons are a kilogram meter per second squared, right? Times seconds. So if you cancel out this second with one of these, your units of impulse are going to be kilogram meters per second. Does that make sense?
Yeah.
Let me get let's get your pencil out and we'll walk through that again for a second. Okay, so your impulse is in units of newtons times seconds, which would be a kilogram meter per second squared times a second. So then your seconds cancel. you end up with units of kilogram meters per second. So, if
You said impulse is represented by J?
right, it's a capital J.
Okay. So what's the representation of joules, just so I don't get that confused? That could happen.
So usually they'll say like J of X, I guess.
Oh, okay. And P is momentum. P is momentum with the arrow over it.
Yep.
Yeah, it's not the arrow over it.
It doesn't absolutely have to. So like see here, they represent it without the arrow. The arrow's there just to remind us that it's a vector. But see right here, so P of X equals MVX, P of Y equals MVY. They'll drop it sometimes. But that's because if you do P of X, that means it's a vector along the x-axis. You know that for sure. So you don't need to remember that it's a vector. Okay. The impulse, so J, is units of kilograms times meters per second. So where else have we seen that unit before?
It's similar to force.
Similar to force. What about it with the momentum? So your units of momentum
Okay, yeah, I guess they're the same.
are kilogram times meter per second. Units of impulse are kilogram times meter per second. So they must be related, right? If they have the same units, they can relate to each other. So how do you think impulse affects momentum?
I don't know. I can see how momentum would affect impulse, I guess. I don't know how we would end up with a square graph of momentum, though. How would that?
Yeah, they simplify it. I think right here they actually.
So I've heard something like this before, where the actual shape doesn't always matter as much as the area.
No, it doesn't. You're right. So we'll talk about that in just a second. But what happens is, so you have a certain momentum going in one direction, right? So this momentum coming here, and then there's an impulse, which was this force over a short time, and it caused it to go the other direction, right? So you started out with a certain momentum, there was an impulse, and it changed the momentum, right? So impulse can actually be defined as, it says right here, it's the change in momentum. So this is the impulse momentum theorem. So J equals the change in P. So J of X equals the change in P of X. The same thing goes for Y too. So JY equals the change in PY. So that means if you have an object with a certain amount of momentum and you apply an impulse to it, that impulse will change your momentum by that amount.
So that's what impulse is defined as, the change in momentum.
Yeah, they're related to each other that way. It's defined, I mean, it's a relation, right? So there's two ways to define it. One is that it's the integral of force over time. So you have this force and it's applied over a certain amount of time. You find the area underneath it, right? But that also, that impulse is equal to your change in momentum. Okay. So what it's saying over here with the box, so if you were to take every value of force in this whole thing, it's an infinite number of force values, but you were to find the average value of this. Did you ever do that in calculus, finding the average value of something?
I don't remember doing that. I mean, I remember taking integrals.
Yeah. So to find an average value, you take the integral and then you divide by the length on the bottom. That'll give you your average value. But this force that is applied has an average force too, right? Just like, so if you're driving down a road and you speed up from 0, and you hit 25 miles an hour and then slow down back to 0, you'll still have an average speed, right? It'll be between 0 and 25, which depends on how fast you accelerate and stuff. So the force will have an average value, and if you plotted that average value across the same length of time, then you could find this rectangle.
And that's how we find impulse.
And it's the same as the area underneath this. Yeah, so that's one of the ways to find impulse.
The easiest way.
Yep, definitely. Typically, I don't think in this class they have you do much integration to find impulse. So like here. So typically they'll give you a triangular shaped impulse graph and you find the area underneath that, or force versus time graph. So like they're usually triangles.